use this, right? Sine square x plus cos square x will be equal to 1. This one we use previously. So actually, if you do some modification, so end up you will get this formula as well. So this is exchangeable, these two. So we also use, let us see. There is one more thing I think we will be using quite a lot. There is sine, law of sines and law of cosine. So these two also use a lot, right? Because with these two, with this normally, for example, on this sine rules or law of sine, so whenever we know two angle and one link length, so we can easily find another link length. Okay, or the other way around means I know two link length, I know one angle, so I can easily find another angle. Right. So for this one, normally we use it to find when we have two link length and angle, so we can find the length of another link. Okay, so you just work on the triangles. So you try to practice it and remember this. So this will help you to solve the questions faster. Okay. So then we will move on to our lecture 1. Okay, let's see. Now we have 109 students. So remember to take your attendance by submitting the vote on the chat there. Okay, so we will continue our lecture 2. Sorry, lecture 2 on this position analysis, because later we'll go into velocity analysis and then to the acceleration analysis. So I think we stop just a second. We stop here on the calculations of this theta 3 and in this case is theta 3, right? For the 4-bar crank sliders engaged. So we will look at how to find the transmissions angles and the total position, the angle for the total position. So first we look at the transmissions angles. Okay, so we look at this mu, right, transmission angle. So it's defined as an angle between the output link, right, and the coupler. So some of you may confuse. Okay, so as I mentioned in this, according to this textbook, so this link A is always our link 2, or we call it the crank, right? So link B is link 3, which is our coupler. So then C is our link 4, and then it will be our rocker in this case, right? So D is our link 1, which is the ground link. We call it ground link, right? Or the fixed ground. Okay. So that's why this one, the link 4 here, they also call it the output link, right? Because this is the place that it will do the work normally, right? In most of the case. As I always mention that we always put a motor here to drive the system. So that's why the output link will be referring to the link 4 in this case. Okay. So it is usually taken as the absolute value of the acute angle at the intersections between the two links. So now we have this link, the link 4. So you extend it, and then we have the link 3, which is the coupler. So you extend it. So the angle between here is the transmission angle, right? So it's a measure of force transmissions at the joint, because from here then we will know how much force will be received, or how much torque will be received in the link 4, right? So this is when the case that this we call it the gamma 1, okay, is less than 90, yeah. So then we will say that the transmission angle is equal to the gamma 1. But when we start to rotate this link A, okay, the link A here, when we start to rotate this link A, okay, to this position, okay, then we rotate it to this position, then you will find out that gamma 2 now is greater than 90 degrees, okay. So how are we going to find the transmission angle? So we will apply this, okay. So it's mu equal to pi minus gamma, huh? So to differentiate between these two cases, that's why here you call it mu1, here you call it mu2, huh? But both are referring to the transmission angle. So we can try to find the transmission angle. Right, so we just for a 4-bar linkage, that's what we have just now. Is actually just a difference between the theta 3 and theta 4. So we take the absolute magnitude of it, theta 3 minus theta 4. So in the case of when it is greater than 90 degree, so we will apply this formula here, mu equal to pi minus the transmission angle, or if you look at the previous diagram, we call it gamma 2. Okay. So if it's less than 90 degrees, so we can straight away take it as the gamma is the mu. Okay. So if you refer back to the previous diagram, it says mu1 equal to gamma. So this is here he label is mu2 equal to pi minus gamma 2. Right? So we have link 2, link 3, link 4, and link 1, which is A, B, C, and D. Yeah? So we can actually use the cosine laws, right, as I mentioned just now. So we can find mu1 with these formulas. So you can go back to the diagram here, right, and then try to explore, okay, with the formulas we have. Okay. So I'm not going to derive this. So for the extended case, right, means that the diagram B here, right, so we can calculate using this. So what we do is basically there is pi minus, because same as here. Okay. And if you look carefully, there is a small difference between the formulas here. Right? One is minus, one is plus. So both of these mu1 and mu2 is the transmission angle, which depending on how our links is position is. Right? So again, I always want to remind that when we study this linkage, you have to think that this linkage is keep moving, so that when are we freezing? So are we freeze it at this position, then we try to analyze, or we freeze it at the position B here, and then we do our analysis. Alright. So that's why we have the formulas for different positions that to be applied. Right? So the minimum transmission angle mu min in the Grashof crank rocker linkage is then the smallest of mu1 and mu2. Okay, so this is the transmission angle. So we will move on to the toggle position. So at the introduction to the linkage, we actually talk about the toggle position. That is where our coupler and coupler and rocker will be collinear. Okay, so in this case you'll find that then your mu will be 0 because the angle between these two links will become 0. There is also a possibility of when these two links is fold together, so means your mu end up will become 180 degrees. That is also possible. So what happened here is when at this case, then your transmission angle is automatically 0, same as this one, okay? Because 0 and 180 is actually serve as a same condition, okay? Same force condition on the linkage. So the other case is when my crank and the coupler is collinear. Okay, so again I keep highlighting this crank and coupler now is in collinear, so we call this angle V. So now V is 0. So when V is 0, then we can calculate this mu. Alright, so the formula is given here using the law of cosine. Right, so because we can build this, we have this triangle, so you can find using the cosine rules to find this. Right, so if we have D, we have A plus B, and also C, so we can easily find the angle of the mu. Okay, so you can go back and look at it. If you can't find it, then you let me know. I will show you how to get the mu. So in the other toggle position, when input rocker A and coupler B are collinear, so this is what dimensions are. Okay. So now we can actually calculate the toggle positions. Okay. So express the transmission angle mu in terms of the link length and the link input angle of θ2. Right, so now we want to link the mu to the θ2. So based on the diagrams we have here, okay, so we can apply the cosine rules. So if you look at that, this is h square equal to a square plus d square minus 2 times the a multiplied with d cos θ2. So we can get this formula. So this is based on the bottom side of the triangle, this one. Alright. So if we can make another formula based on the upper side of the triangle here. So we get this h square equal to b square, alright, over here, plus c square minus 2bc. Then we have the angle mu here. So then we can link both of these together, right, using the h. Right, so we will make them equal. So that's why we get this formula. So just try to rearrange. Then I will get the relation between the mu and the θ2 with all the link length parameter here. Okay. So to find the maximum and minimum value of the input angle θ2, then we can differentiate the formulas and the derivative of the θ2 with respect to mu. Then we set it to 0. Right? So we do this, then we set it to 0. Right? Because once you set it to 0, you will be able to find maximum and minimum value. We always in the mathematics class, we say dx over dx dy equal to 0. So we will find max and the mean value. So this is the same concept. So we differentiate it, we set it to 0, so we can find the max and mean value. Okay. So the link length A, B, C, D are never zero. So remember, because this is a linkage. Okay? So the expression can only be zero when mu sine mu is zero. Okay? When this is zero, we cannot set this to be zero. Because if you set this to zero, answer will be infinity. So we can only set the top is zero. So this will be true when angle, because how to get sine mu is zero, so you can either get your mu is zero or 180 degrees. Okay, so when we set mu is zero and 180 degree, what happened to cos mu? It will be either plus or minus 1. So substituting these two values of cos mu give a solution for the value of theta 2 between the 0 and 180 degree, which corresponds to the total position of the a triple rocker linkage when given from one rocker. So this is where we will get our theta 2. Okay. So this actually this is a mathematical calculation. So if you are good in drawing, okay, because this is position analysis, you can always sketch the diagram according to the dimension with the scale scale diagram. So you can also solve your problems. So if you have a graph paper, so you can actually draw the linkage, the link length and the angle accurately. Then you can find the all the angles and so on. This is for position analysis. That is could be an easier way if you are not sensitive to the formula. Then you can draw it. Okay? So the other way is if you have AutoCAD or SolidWorks, sometimes you can also use them to do this analysis. You just draw the link according to the dimension and the angle. Then from there you can measure whatever angles you want, and also the link length that you are interested. Right? So there is a graphical way. So the one we explain here is on the calculation or the formulas method by using the formulas. Okay, so this end our position analysis. So then we will move on to yeah, so I can turn off. Then we will move on to the velocity analysis. Okay. So again, velocity analysis, we can also use a graphical method. The instantaneous center of velocity, velocity analysis with instant center, and then what are the mechanical advantage on here? Analytical velocity analysis. So there are a few ways we can solve the problems. So we will look at one by one. So first of all, we will start with the crank. Oh. Just a second. Okay. So first of all we will start with the crank. Yeah. So which is the link 2. Right. So our crank always rotate at 0.8. So this is what we consider pure rotation motion. Okay. Pure rotation motion. So what you will be expecting is that we will only have one velocity component, which we call it VPA, right? Okay, because the velocity is always tangent to the rotation here, so it's a tangent. Because this link or the point P here is will only do this circle, right? So upon we know the theta, we will know the direction of this VPA. Yeah? So let's look at what the textbook say here. If we represent the position vector of RPA, which is this one, as a complex number in polar form, so we have PEJ theta. So uh, the radius P with the angle of theta. So we can easily differentiate in to obtain the following here. VPA is we'll get the P omega J E J theta, right? Because we must have omega first, right? Or which is given here. So the direction of the V will depend on the direction of the rotation here. If we say now the VPA is going this direction, so our omega will be in the clockwise. Right? So the velocity vector will rotated 90 degrees from the angle theta of the position vectors. So in the directions detected by the sign of the omega, so means that here you will have a 90 degree change here, right? So that's why when we know the theta, we can actually know what is the direction of this VPA. So by using the Euler identity, so VPA, we can break it into x and y component here. Okay. So we have P omega j cos theta plus j sin theta. So when we multiply this complex number j in, so we'll get j cos theta here. So j square, you'll get -1, because for complex number, this is square of -1. So that's why here you'll get the negative. Okay. So there is in this diagram there is some missing. Even in this is from textbook. So this is supposed to be VPA. That's why you shouldn't have two VP there. So in this case, this is VPA. Okay. So what he tried to explain here is these formulas is velocity at point P, which refer to point A. The reference is at point A. So in the case when my A itself is moving with the velocity VA, so what will happen to the velocity here? So my velocity at point P will be called VP. Okay. So VP is actually the VA plus the VPA. Okay. Because this velocity always refer to point A. So now if my point A have a velocity, so I have to add the velocity of point A in order to find the absolute velocity of the point P here. Okay. So another thing is for the whole course, we always assume that the clockwise angular velocity is negative, counterclockwise is positive. So this is what I written just now. Okay, so please make some correction on your notes here. So we have VPA, this one. So we can write it in. This is exchangeable, so depending of which one you are trying to find out. Okay, so you are trying to find VPA or VP, so we can change the formulas format. So case 1, 2 points in the same bodies. So then we can find the velocity different. Case 2 is 2 points in the different body, then we will find the relative velocity. Okay, so then we go to the next one here. So next one is to find the coupler. Let me see. Yeah, because the first one, this is graphical way if you want. Okay. So when it comes to the this section, we are looking at the coupler, which is link tree. Yeah. So before we start, you have to keep in your mind when we say link length of the link tree. So when we analyze the linkage, do this linkage analysis, we always have to find where is the join. So for example, the link 2 will join to the ground at this point O2 here. The link 3 and the link 3 and the link 2 will join at the point A here, right? But then link 3 and link 4 will join at the point B here, right? So link 4 will join to the ground at the O4 here, right? So that's why when we try to find the link length, this point to point, so this is the link length, okay, for link 2. So from point A all the way to point B, this is the link length of link 3, right? And then for B, or normally we call it for O4 to B, that is the link length 4, right? Link length for the link 4. So because of the functionality of the link, so sometimes the linkage can have a different geometry, right? But the link length is still the same from joint to joint, yeah. But actually we can modify the geometry of the uh, of the link, so that to serve our functionality purpose. So in this case, for example, it create additional point C here that actually may be used for some purpose. So we can set it away from the link length. Right? So that's why from here, then we can use this velocity analysis to find the velocity at any point on the link as well, not just at the joint. Yeah? Right? But for sure, the first thing we want to find is always the velocity at the joint here. Right? So for example, O2 and O4 is zero velocity because it's a fixed joint. Then we have this point A and B. Right? So now let us look at the point B here, or more towards the VBA. Yeah? Okay. So if we look at the coupler itself, just the link tree, now assuming that the omega is counterclockwise, okay, then my velocity will be in this direction, VA. So because the point O2 is not moving, so we can just call it VA. So you don't have to call it VAO2, right? Unless the O2 is moving, then you have EAO2, then you draw this one, right? So this is the actual velocity because this O2 is not moving. So we can draw this line. Okay. So if this is the theta, this is theta 2. So how you get the angle of this? So what you have to do is that at this point, you draw a horizontal line. So this is theta 2. This should be 90 degrees. Or maybe I use other color. Okay, so we have a horizontal line. we draw a theta 2 here, because there is an angle given here, and then we set another 90 degree. That is where we can get our VA. Okay, so then we for the time being we do not know where the VBA is, okay, but we can know where is our VB, because again point B here is rotate with respect to O4 here, and you only do pure rotation. So you have to use some imaginations here, because now if I rotate my link 2 in the counterclockwise here, what will happen to our link 4? So link 4 will have to move same direction. I cannot move the other direction at this setup, or at this instant moment. So that's why my VB will follow with a 90 degree here, right? That's why then I can draw a line, which is this one, the PP line, and then I can draw this VB. Okay, this is VA. But the VA, because if you were given the omega and the theta, so sure we can find the VA value, right? We can find this value, so we can draw it with the correct angle, which is given theta 2, and we set the 90 degree here. So the length of this, again, this is a scale drawings, right? If you want to do a graphical way, so this is the magnitude of the VA, okay, which we can calculate it based on this omega and the length. We never mention what length here. If you follow previously, this is P, the length here. So VA is as simple as the P, or we can call it RA omega. Okay, so that is velocity, the magnitude. Then the angle is given, so we can draw this one. But this one we do not know the magnitude, because in this case we may not know what is the omega 4. Okay, so we just draw a line, but then we have this point. Yeah. So now what we have to do is to find where is this QQ. So again, this is the length 3. Okay. And I try to erase some of the things here so that we can see clearer. Okay, so we have point A here, point B here. As a 4-bar linkage, our reference of link 3 is at point A here. So this is theta 3. So now if we trying to find the VB relative to A, okay, so it will be either going here or here, okay, because this is depend on the omega 3, right? We do not for now we do not know where because we haven't done the analysis, we do not know where the omega 3 is rotating, but for sure we know that it will the VBA will be 90 degree to this link length 3, yeah, right? So either it go up or go down. So that's why based on here, or how you draw this line, we know that this is same when you have theta 3 here, so this is also theta 3. So then there is 90 degree there. So what means here is you have a horizontal line, you set it to theta 3, you set it to 90 degree, then you draw this line. You just draw it long enough. So now we find out that only coming down, it will meet the VB. So means we are quite sure this is the VBA, this is the correct one, right? And then based on this one, we already know that my omega 3 will be in the clockwise direction. Right? So then after you complete this triangle, you can measure its magnitude. Right? To know is VBA, what is the magnitude of VBA, as well as the VB. Okay? So this is a graphical way. Yeah? But based on the vectors diagram here we can also write the formulas. If you don't like to draw the scale diagram, then we can always calculate VB is equal to VA plus VBA. Yeah? Okay? I can keep erase because after that you can always refer to video to see what I have drawn. Not like the physical class one I erase, then you may not know what I drew previously. Yeah. So what happened here is to find the VB here, to find this. So we can always take the VA plus the VBA, pass them together because this is vector. This is a vector to complete from this point to this point. Yeah? So similar things can be done in order to find the velocity at point C. Yeah, we want to find the VC. Right. So again, VA we know. Right. VA is a known value. As long as we know omega, we know the radius of link 2 and also the theta, so that we can know what is the angle here. So this is theta 2. So we set another 90 degrees because the velocity is always tangent to the perpendicular to the radius of the link. So now we can find the VC. So what happened here is now we can find VCA first. So this is a VCA because why he choose going down? Because based on the previous pitch, we know that omega 3 is clockwise. So then we can quite sure it's going down here. So then we have the link here. We have a theta 3 here. It will actually give you another angle here. Right? Maybe I call it now theta C. Right? So that's why if I have this, this is theta 3 plus theta C, right? And then you add her 90. So you can draw this line, RR line, right? Which is same as this one. Okay? So you can draw the RR line, then we go, because of the omega 3, then we know that going down is the direction of the VCA. Okay? So in this case, how to find VC over here? Because we have from the previous VB analysis, we already know our omega 3. So we can find the VCA is equal to, maybe I call this RC. Yeah? It's a RC omega 3. So we know the magnitude. Okay? What is the velocity of it? Then you can draw the magnitude of it. Okay? So then you can join this point to this point to form the VC. Right? So this is how you do the graphical method on this analysis of this point C here. So if don't use this graphical method, you can use the formulas. So we can find VC from VA and VCA. But anyhow, you still have to use this to find the VCA. And also remember, this is a vector calculation. So end up this will have the XY component depending on how you calculate it. or you can use the complex number method. Right? So either you put it into the x and y, or you can calculate it accordingly. Let's see example here. Right? So you look at the geometry of this, you see that it's a cylinder or a disc here, and we have a link here, and we have some link with some geometry here. Okay. Okay. I may give you questions which is similar to this, just to confuse some of you. So if to make sure that you understand what we mean by the linkage analysis. Because if when you get problem like this, the first thing you will try to do is you try to find where is a fixed point. So I have O2 here, I have O4 here, okay, and then I have my link 2 because my point A is here. So this is my link 2. Right? You don't bother about the circular disc. So you just make it into the line diagram. So it will be easier for you to analyze. So there is my link 2. And then my point B here. So if I connect A and B, this is my link 3. And then I have my B and O4. So I connect it. There is my link 4. So my ground link will be this one. So there are different way you can do it. So either you solve the problem exactly like this, the diagram like this, or you can actually set this axis to be your horizontal axis X. So you can see you put the X and Y here. So means that if you are on your monitors or you print it out, so you can rotate this O2 to O4 into horizontal line, then you start to do the calculation from there, right? Or else then you have to keep it in this way where your O4 will have some offset, or your D will have angles, which is offset from the global axis here, X and Y. So just up to how you want to solve it. So the link length information is given here. So we have L1, L2, L3, L4. Okay. So L1 is referring to the ground link, means the distance between the O2 and O4. Then L2 is link 2, the length. And then we have link 3 and link 4. So this is the link length. Right? So what we have to do is to find the velocity of B and the angular velocity of theta 3, link 3 and link 4. Okay, so VA is always one of the easiest to find. So he also give us the omega 2, the angular velocity of the link 2. So he mentioned counterclockwise. So means that my omega 2 is positive, counterclockwise, radian per second. So in this case, if we are using the graphical method, so what we can do here. So this is all the information given just now. Theta 2 given 57 degree. And then the input crank angular velocity given 20. So there is another angle given to the link D here. So it's minus 36 degree. So what it means here is minus 30. What is that? 36 degree. Yeah. So if you are rotating the line O2, O4 to horizontal, means that your theta 2 will become 57 plus 36 degree. Right, so it becomes 90 93, yeah, 93 degrees, yeah. Right. So, but let's see how the textbook solve for this, right? So actually you can ignore all these lines, right? You just focus on this one, this one, this one, and this one, right? So VA, as I mentioned, is always very the easiest to find, right? So we have the length 40 mm. So I can find my VA is 40 mm, which is 0.04 multiplied with 20 radian per second. So so he actually used millimeters. So I change it back. So 40. So we get 800. That's why here you use millimeter, we'll get millimeter per second because this is radian per second. So this is millimeter. So just now if I use 0.04, end up I will get meter per second. Right? So here you use millimeter per second, it's fine. And then we can find the theta A, because this is going here counterclockwise, so my VA will be here. Okay, so the angle that we are trying to find, right? So it should be theta 2 plus the 90. Okay, that's why your theta A is theta 2 plus 90. Yeah, so theta A, what we will get is the 57 plus 90. So it's 147 degrees. Yeah. Okay, so that is the angle. So in this case, we are solving it without changing without making this axis as a horizontal axis. So from there, when we have this value, actually we can find we already find VA. So this is VA data. So we can say VA is 800 millimeter per second at the angle of 147 degrees. Okay. So measure from horizontal up, so 147. So now if you want to find the VB, finding here, let's see, yeah. So we know that VA is this graphical method. So you just draw something, some scale. So in this case, take this scale. You can see that 400 millimeter per second in I'm not sure how, because now I will paste into PowerPoint, so it may not follow exactly. I can't use ruler to measure here. So when you draw on your own, then yeah, you can specify this scale. Maybe 2 cm here, or 1 cm is 200 millimeter per second. So you draw the 800 millimeter per second here with the angle of 147 degrees. So you have to use your protectors, right? So just give some idea how you draw it. You can use your compass here. I mean you put your needle here and then you draw a line. For example, now if 1 cm is 200 millimeter per second, so you draw a 4 cm, right? 4 cm radius. So you draw it here. Then you use your protector to set the angle, then you start to draw a line. So we know that this point is the end of the VA. Then the next thing is we have to draw where is VB. Okay? Because based on here we can find our VB when we know that the uh, when we have this. Okay, that's why you have to, this is the velocity analysis. So you have to do the position analysis here. So when we have this line, so basically you will be able to find this theta 4 first using the position analysis. Right? So when you have this theta 4, that's where you can get this direction of the VB. Okay? So in this case, the direction of the VB is 6.4 degree in this direction. Okay, so to define whether it go here or go there, so again we can look at the diagram here. So now this one turn this direction. Okay, so this has to follow. It cannot go the other direction. Okay, because this link is fixed. The link tree is fixed, so it must come here. That's why now we specify this here. So again, at the beginning, we do not know this value. So we only know this VA here as second one. So we have this line. So there is another line we have to draw, which is the VBA. Right? So this is this one. So you have to solve the position analysis in order to find the theta 3. Right? So you have to find the theta 3. I think I should clear this. So you have to find this is the link length. You have to find the theta 3 first. Once you find the theta 3, then you set the 90 degree, then you will find this VBA, which actually gives us this 85.4 degrees. Okay? So then you draw another line. So you have this line and this line cross. Right? So from here, then you can measure the magnitude. Right? So you use inches. So I believe this is 1 inch. So then you multiply back to this value in order to get the VBA here. So VB is taking this one, the measurement, 1.79. So you get VB. This one 1.293. So you will get the VBA. So this is from graphical method. Okay. So once we get the VBA, we can substitute into here to find the omega 3 as well. Then we get the omega 3 is 5.388 radian per second. So we can also find the omega 4. We take the VB, put in here. So we can find omega 4, which is 5.869. So we will get all the value. At this point, any questions? You have to try. You cannot just look at the slides and you expect you know how to do in the midterm or in the final assessment. You must try to practice, because this one needs some logic thinking in behind. It's not substituting formula then you will get answer. Right? So you must try to understand the relation between all these linkage. That's why that is very important for you to practice, right, to do it. Okay, then we move on. Since there is no one is texting me here, so we'll move on to what we call here the instant center of velocity. So the definition of instant center of velocity is a point, right, common to two bodies in plane motion. Which point has the same instantaneous velocity in each body. So instant center are sometimes also called the centros or pools. So the combination formulas of for n things taken r at the time is c equal to this function. So for our case, the r equal to 2, then it can easily reduce to these formulas only. Okay. So for a 4-bar linkage, so means that c equal to 4 minus 1 divided by 2. So we get 12 divided by 2. That's why we get the 6 instant center. So if we have 6-bar linkage, so we can calculate 6 minus 1 divided by 2. So we get 30 divided by 2. That's why we get 15 instant center, right? Alright, one of the rules where we will be using is the Kennedy rules. So any 3 bodies in plane motion will have exact 3 instant center, and they will lie on the same straight line. Yeah? So given a 4-bar linkage in one position, right? That's why whenever we solve this, we will actually fix it in one position. So normally this will define the position of it. So theta 2. Then we try to find all the instant center using the graphical method. So what we do is draw a circle with all link numbers around the circumference as shown in the figure A. So this is the one. So we have 1, 2, 3, 4 here. Okay. So you look carefully here, it mentioned this is I12, I23, I34, I14. Okay. Alright, so now we locate as many instant center as possible by inspection. All pin joint will be permanent instant center. Alright. Connect the link numbers on the circle to create a linear graph and record those IC instant center file as shown in figure A. So identify link combination on the linear graph for which the instant center has not been found. So and draw the dotted line connecting those 2 link numbers. Identify 2 triangles on the graph that each contain a dotted line and whose other 2 sides are solid lines, right? Representing the instant centers already found, right? On the graph in figure B, link number 1 and 3 has been connected with a dotted line. So this line form one triangle with sides 1, 3. Right? That is where what is mentioned here. This is 3 here. So you find this 1, 3, and then 3, 4 is this one. 1, 4 is this one. So you can see that there is forming a straight line here, and another side of 1, 3 again is a 1, 3, 2, 3, and 1, 2. So we form another straight line. Alright, so it lies on the straight line. So also the instant center of 1, 3, 2, 3, and 1, 2 will lie on the different straight line. So there is one straight line here and one straight line here. So on the linkage diagram, draw a line through the 2 known instant center that form a trio with the unknown instant center. So what it means now is now we draw between these, the 2, 4. Okay. So means we take this 2 and 4, we draw the line to form this I24. So this should be I24. So then we will get this I24, I12, I14 is here, and then I24, I23, and I34, another line. Right? So we get this it didn't mention here. So we have these two lines. So when we come to the number 5 here, connect link number 2 and 4 with the dotted line. This he mentioned already. 2, 3, 2, 2, 4, 2, 3, and 3, 4. This is one line. 2, 4, 1, 2, and 1, 4. There is another line here. Okay. So on the linkage diagram, draw a line through the two known instance center that form a trio with the unknown IC instance center. Repeat for the other trio. So in figure C, a line has been drawn through the I12 and I14 and extended. So I24 must lie on this line. So another line has been drawn from I23 and I34 and extended to the intersect the first line. So by using this Kennedy rule, so instance center I24 must also lie on this line. So their intersection is I24. If there were more links, this procedure will be repeated until all the instance center were found. Okay. Just now we say that 4-bar linkage has 6 instance center. So that's where we get the 6. 1, 2, 3, 4, 5, 6. So this is how we find the 6 instantaneous center. So now we're trying to do examples here. So instead of continuing looking at the 4-bar linkage here, we look at the crank sliders. Okay. So again, this will consider a 4-bar crank slider because there is a mesh here. Okay. So draw a circle with all link number around the circumference. Right? So this one is referring to this. Then we'll locate the 1, 2, 3, 4. So we'll locate the 1, 2 is here, 2, 3 is here, 3, 4 is here, 1, 4 is this one. Okay, so you will notice that this one you will get infinity because it's just perpendicular to this sliding surface. Locate all instance center possible by inspections. All pin joints will be permanent instance center. The slider joint instance center will be infinity along the line perpendicular to the sliding axis, as I mentioned here. There is 90 degree there. So connecting the link number on the circles to create the linear graph and record those instance center file as shown in the figure A. So now we started. Okay. So we start with this. Okay. So we start to look at link 1 and link 3. Link 1 and link 3 here. So we can create these two lines. Okay. So we will find the I13. Okay. So I do it slightly faster. Then we will find the, because that's how this one is to find 1, 3. So later when we come to here, we find the 2, 4. Okay, which complete the 6 instance center. So then we have a link 2. Okay, so in this case, the link 4 here will be slightly different. We will actually utilizing this line, right? Because now this is we don't have the physical link 4 here, so we are taking this line that to form the instant center of 2 4. Okay, so that actually complete this. So we will have 1 2 3 4 5 uh, basically 6 here, because the I 1 4 is infinity, so it means it will go along this line, right?
So I still
Yes,
confused about how to find the dotted line.
on here.
Yeah, because 4 to 1 is infinity, right?
Uh-huh.
So how I find the I13 dotted line?
I13. Just a second. Okay, I13 is normally because we know that the 1 4 is basically is this. Means that I14 is along this line only because they are infinity, so means that it will be stay within this line. So now if I trying to connect it,
But then
it
the angle is assumed by ourselves,
no, it's
perpendicular.
perpendicular to this surface.
Okay.
Okay, so this line is perpendicular to this surface. That's why it actually built up. If you look at it, this is 90. So you draw this line in order to go up, and you draw another line from this link 2 here. Okay. So means actually we are trying to join this link 1 and the link 3 lah, right, using this triangle. Okay, that's where you find the I 13. The one it may be more confused is actually this one. This one is more straightforward. You have the link 1 here, link 2, 3 here. So you just join it, then you form the I13. But this is when we want to find I24 is actually because we should actually find this. If we look back to 4 bar, so we have link
Yeah.
2, we have link 4
Yeah.
here, okay? So we join them. Oh, so we join them. That's where we find 2 4. Okay? But the problem
Yeah.
now here is we have link 2 here.
Infinity.
There is no link 4. Alright? So what happened here is then how are we going to find this I24? Okay? That is the more I believe this is more confused. Okay? So maybe we go to the description here. Uh, let's see. So what he mentioned here is we connect the link number 2 and 4 with the dotted line on the graph as shown in the C. This line form one triangle with the side 2 4 2 3 and 3 4. Where is 2 4? This is 2 4 2 3 and 3 4. Okay? So what it means here is you are extending this line. Okay? This is same as the previous one, right? So we're extending this line. Okay? Same, So now what the difference here is how to get this line. This line is basically parallel with this. Okay? That's why if you find out this is 90. Okay? That is where you will get the I24. Okay? That's why now we say, you see the other one will align with the 2 4 1 2 1 4 because it's same direction of 1 4. Okay, you may have to digest a bit. Okay, so this is how we get
I get it. Thank you, sir.
you get it on the slider. So there is a slightly difference between the 4-bar linkage and 4-bar slider. So this is a tricky part here on the 4-bar sliders. So this line is still the same, but then we don't draw this line anymore because the I14 is here. So we put another parallel line passing through the I12 so that it form a straight line there. Okay. So this is how we find the I24. Okay. Let me see what is the time now. So let me see how we use this instance center. Okay. So this part is just to find the instance center. Okay. So after we get the instance center, then we can start to do the calculation. But honestly, the instance center of this I13 will be used. The I24 normally I don't think we use it in our calculation. Right? Okay, so now if we look at one of the examples here, just now the 4-bar linkage, we find the I13 is there. Actually, there is another I24 here. Right? So as I mentioned, most of the time we are using the I13. Yeah. Right? So again, the same question is given. Same question. We given theta 2. We given all the link length. Okay. So we given the omega 2. So the green color is given. So link length we will given the A, B, C, and D. Yeah. So link 2, link 3, link 2, link 3, link 4, and the link 1. So then we can calculate this VA. Okay. Because of this instantaneous center, again, this one have to do it in graphical way. You must measure. You must draw in the scale and then measure. Because when we have VA, we have to measure this line. What is the length of this line? Okay. That's why they call it A13. From point A to point 1 I13. What is the length? Okay. So because we have omega is radius, sorry. Because we have velocity is radius multiplied with the omega, so we can find omega is velocity divided by the radius. So in our case here, the radius is from I13 to A, and then the velocity we already have is VA. So once we find here is basically we will be able to find what is the, even though he draw it here omega 3. So basically it is omega 3 or the rotating angular velocity of this link 3. So we will find out this is clockwise. Right? So you will expect that when you do calculation, you will get the negative value. So the advantage of this is by looking at this drawing, we can very fast we find omega 3. So once we find omega 3, basically we can find a lot of other velocity, including the VB, VC prime. Sorry, not VC prime, because I looked at the angle wrongly. So 90 should be to this VC. Okay, yeah, VC here. the VC prime is referring to this line, right? So we can easily find VB. Pick another color, right? Just find this length, right? The length between B and I13, right? This one. So we measure this length, multiply with the omega 3 we find on the top there, so we can straight away find the VB, right? Once we get the VB, then you can refer back to here to find the omega 4, right? Because omega 4 will be again velocity VB divided by the radius of this, right? B04, so B, sorry, you never mentioned 04 here, right? So we'll get the omega 4 as well. You see, we can get omega 3, VB, omega 4, right? By just completing this graph, right? So if we are interested to find the VC, so again, you can measure this line here. Right, then you can get this VC. Right, VC is CI13 multiplied with the omega 3 that we found, right, from here. So you'll get the VC. Right. So by having one diagram, so we can analyze the velocity at any point. So as long as this is the link tree, we can find velocity at any point, right? You want. You just the key is you have to find the distance between the instant center of this I13 to the point that we are interested. Because later when we're trying to solve the dynamic linkage, we may have to find the velocity at its center of gravity. So that's why then you can use this radius, and then I can find my velocity of VCG of this link tree, right? Easily, right? This is one of the way, right? Most of the time, ended a lot of students will use the formula because I think they still not prefer to draw the scale diagram. This one must be in scale, right? So again, have to highlight here. It has to be in scale diagram. So we look back at the same question as just now we do. All right. So everything is the same. So what happened here is now we draw the instantaneous center. So again, this is the I13. So if we really want to find the I24, so we are extending this line and also this line. So we will find I24 here, right? But in our case, we don't use this, right? So we only use I13, right? So now we measure the distance between A to I13 is 148.7 millimeters, and then B to I13 is 133.192, right? Theta is actually measured once I maybe we let's see. Let me remember the numbers first. So we have 40, 96, 122, and 62. So actually how we are trying to draw here. So you can always start with O2. Okay. So create your line, horizontal line, vertical line. Then we start with the angle. We can start with the angle of theta 2. So in our case here is 57 degrees. Then you draw a line. Okay. So you have to measure, in our case, this is 40 mm. So we create this 40 mm here. So the other one, D is 36 degrees. Yeah? So again, we draw a line. Based on the length, this is 40 mm. This is, what is the number? Because I cannot turn back and forth for my, let me find the questions. Or anyone can give me the numbers. There is the number. Okay, I found the number. So link 1 is this will be 162 mm. So we have these two. Then what you do is I find this point and this point. Yeah? So you will take compass. I believe we call it compass. So you set a length of 122, the skew dimension that representing this 122 millimeters. Right? So you pin here, then we trying to draw the circle. Right? So then another one is 96 mm. You pin here, there is a link 3. Right? This is link 3. Yeah? This is link 4. So we try to make another line that actually will find this intersection. So that's where then we can connect. This will become link 4. We connect. This will become the link 3. So this is the first thing you have to do. Based on the data given, we create this scale diagram first. So this is a scale diagram. Then only we will start to do the instantaneous center, the I13. Okay? Then you start to measure all these dimensions. Okay? So it's not simply draw. Okay? So that is how we will end up getting all these dimensions, including the angle. Right? Because that's how we draw all this. Right? Including the theta 3, we can also get from the diagram, right? Just draw it up. So again, we do a simple calculation to find the VA, right? So once we get and also is angle, right? So once we have the VA and the A13 here, so we can find omega 3, which is 5.38 radian per second. Okay? So because VA is going this direction, so now if we referring to this point, the angular velocity of link 3 will be in the clockwise. Okay? Then we can find the VB, right? So we have the distance of this one we find here. So multiply with the angular velocity that we found. So we get 716.6 millimeter per second.
So why clockwise?
Which one? Omega 3. Because you will see here, omega 2 is counterclockwise. This is given. Okay? So my VA will be like that. Right? So now if I take this instantaneous, point A must still go this direction, I cannot go opposite, then it will again what happened here. So it will go like this. So in order to make this motion, your angular motion will be in this direction. That's why from here then we can define where is the omega 3, either clockwise or counterclockwise. So based on this, so it's moving here, omega 3 must move here, so that I will get same info. That's why when we get omega 3 here, then automatically when I try to find the VB here, VB is along this line 90 degree. Right? So automatically I will know it must go this way. It cannot go the other way because of this. Right? They have to be moving together. The omega 3 direction of omega 3 is from here. You have to find out. Right? When you say scale, because there is a student asking in the chat there, so I try to answer. So his question is, he thought that we try to avoid using the scale drawing method as error tend to be occur. Yes, you will get depending on how accurate you draw it, so you will have certain amount of error, but it's fine depending on for example, to answer my question, it is fine that you use the drawing method because this is a proven method. So it depending on how fine is your scale. Okay. So for example, you can draw it in the SolidWorks, then you will get a very very accurate result instead of saying error. Okay. When even though the other question is can we label the omega 3 as a omega 1 3, yeah? In our practice here, or referring to the textbook, we don't use omega 1 3, right? Because even though now we are referring to this even though now we are referring to this I13, but actually the angular rotation is for this link 3. That's why we only emphasize this as a omega 3. Right? So still use omega 3, don't confuse yourself. If you put more and more label, then we already have a lot of symbols and numbers in this mechanics of machine. So don't increase the labeling. Yeah. Right, so just keep it as omega 3 because this is representing the angular rotation of this link 3. Yeah. Right. Okay, so move on here is VB. So we find the velocity here. So the angle, if you have the protractor, then you can just measure the angle. Right? So you can see that this the textbook can get a very fine numbers. So if you have SolidWorks, you can try to draw it and then measure the angle, then you will get this kind of answer. But if you draw it using your pen and your normal protectors, then your result maybe end up is only 1/8. For example, it could be 1/88, right? It is fine, right? It is fine, right? For this scale drawing, right? If you are using ruler and pencil, right? It's acceptable, right? Or for the solution of the question, right? Even though you might get some error. Then we can also find the omega 4 because once we have VB, right, we divided by the link 4, right, the length of the link 4. So we can find that omega 4 is 5.874. So some of you may say why is counterclockwise. So let us come back here. We know that this is VB. So now the rotation of the link 4 is referring to this O4. So it will do this. Omega 4 will do that. So that's why it's counterclockwise. Okay, we will continue. Right. The angular velocity ratio. So the angular velocity ratio, or mv, is defined as the output angular velocity divided by the input angular velocity. So for a 4-bar mechanism, is expressed as omega 4 over omega 2, because this is the link 2 is the input, link 4 is the output. Right. So from geometry, then we can define this. Right. So what it means here is, instead of you actually use this V to link it. So what he did is he draw this line, set perpendicular to that actually will cross the O2 to become VA prime, and then set another one over here to cross the O4 to become VB prime. Right. So what it means here is then he will set the distance here, the A prime to O2 as an effective link 2, B prime to O4 here as the effective link 4. Okay, that is where we have here, this one and this one. Okay, so you multiply with this angular rotation. So this will actually set as a principle of transmissibility. Yeah, right. Actually, this can be applied to the gear. So if you look at this, what is the angular velocity ratio? This is gear speed ratio. It's the same thing. Right? So in another way, I can mention that or when you freeze a gear, right? So actually it can become, or it can representing the motion at that point as a 4-bar linkage. I think later we will see some of the example in this way. So if we're looking at the angular velocity ratio, so we can use this. So now what he did is he used this as a effective link 2 is here, effective link 4 is here. Right? And then the other one is a mechanical advantage. So we call it MA. So the power in the mechanical system is T times omega is force, actually is force times velocity. Right? Or here is torque, because it's a rotation, is torque times angular velocity. So we have the input power and the output power. So the product of torque to the angular velocity is power. So we can find the mechanical efficiency if the P out and P in is different. So P out divided by P in will representing your efficiency of your system. So normally when we are solving it, we can ignore the efficiency first. Right? So we can just equal them and then do the calculations here. So mechanical advantage is the force output divided by the force input. So because torque or we call it T out. T out is force out times the R, the output radius times the output force. So I can also write F out is T out divided by R out. So that's why F in is T in divided by R in. So what we do here is we substitute this, I will get T output divided by R output. So when we divide, we can say multiply R in over T in. So that is where you get this one. Okay. So then we can substitute this into the formulas here. So in order to get this, right? So it will be omega in over omega out multiplied with R in over R out. So this is a mechanical advantage. So this one actually the angular velocity ratio and mechanical advantage actually you have looked into it in your, it should be in your mechanical engineering design, the MED. Yeah? It's the same thing. It's just that the books call it slightly a different name. And then this is what we call it the ratio, the input and output ratio. Right? Maybe I touch a bit on this analytical method. So some of you may feel like a graphical one may lead you to a very high error. So you can also opt for this analytical solution. No? So again, in order for 4-bar linkage, we will try to find from here to here. So when we draw the vector loop, we actually draw this. This is R2 plus the R3, we will reach the point B. So the other path is R1 plus the RB, we will also reach point B. So if we write it, right, this is position analysis, so we can write the vector in this way. Right? So means the R2 plus R3, R2 plus R3 is on or basically equal to R1 plus R4. But if you move them all to the left side, so this is the formulas that we get. Then we can write in the polar or the complex numbers format. Right? So again, we can. Right, so this is the position of the linkage. So if we differentiate it with respect to time, then we will get the velocity function in terms of vectors. So if you look at here, this one, and this one, representing the omega 2, omega 3, and omega 4. So that's why then the formulas can be simplified. So we get this. Okay. Then we can do calculation. This one already explained how to get these vectors. Right? And we have VA, VB, and VBA. So we can, instead of writing this, we are actually, you always see we write it this way. Right? VB equal to VA plus VBA. Right? You can memorize this. Right? So VA is this, right? VBA is given as this, and then VB is this one, right? So we can substitute it into the formulas. So we substitute VB, VA, VBA. So we will get this. And this is the substitute into VA plus VBA minus VB equal to 0. So you use the Euler identity, you expand to the x and y component, x and y component, x and y component. That's why then you will expand it to this format. Then we will break into x and y component. So you will get this x and y component here. So you can solve it separately. So you can solve the two equations in order to find the omega 3 and omega 4. For the questions is, the book say VBA is actually same as VB slash A. It's the same. Right? At different point they skip normally in the diagram they skip the slash. This is the textbook problem. Right? If you look at the textbook, normally in the equation they will keep the slash. But when you go to the diagram, normally they will skip the slash. I think it's because of they can't put the things in when they try to make the diagram. Right, so from here you just follow the formulas. Right? If not, you can go back and try to derive it. Right? It will, but honestly, we can just apply the formulas here in order to calculate the 4-bar linkage, calculate the omega 3 and omega 4. Right? Depending on student, some of you will dig all the way down to the fundamental and to understand it. Some may just want the final equation to solve your problem. Right? So that's why from here then we can once we get the omega 2 and omega 3, so we can actually find all the velocity we want. Okay, over here. Okay, because once we get omega 2 and omega 3, we can actually find the value. For sure, this one normally is based on the data given. We already can find this. Right? We already can find VA. So VBA and VB we have to find based on the omega 3 and omega 4 that we find from here. So that's why you will see omega 3 and omega 4 will be find based on the omega 2. But then your theta 2 and theta 4 and theta 3 is from your position analysis. Right? Because normally questions will be giving you all the link length, which is A, B, the angular velocity for link 2, the theta 2. Right? As well as this, the blue color circle is normally given in the questions. So the red color underline is the one we find from the position analysis. Right? Then we will find the omega 3 and omega 4 here before we can find the velocity for VBA and VB. Right? So it's a continuous. That's why I told you I will start from the position analysis first. Right? Then only we can find the velocity analysis, parameter. Once we have velocity, then only we can find the acceleration. That's why the next topics we will look at is acceleration. So I will leave this example on Wednesday. Okay, so we will stop here for today. If you have any question, you can always ask. But some of you may ask me through the Friday night, Saturday, Sunday. So my response will be slow during the weekend time. Okay. So hope you understand on this. I'm also working, so my working hours is Monday to Friday. So the rest of the time I will respond to you if I have time, and also log into the Microsoft team. Okay. I think thank you very much everyone for today. I will stop the recording now. You just